So now you can see that now this X vector field began to make sense. They are nothing but the derivative of these functions, the W functions. Now if you put this into this system, now suppose here I'm trying to make trying to simplify this notation, something called L equals to, so I'm going to simplify this notation, okay, these things. So L vector, so you are using the I don't remember what notation should be. Yeah. So Lj eta 1 and eta 2 so equals to Lj1 eta 1 eta 2 Lj2 eta 1. So each L has two components. If you write this out, it has two components. So this is equal to L tilde F plus eta 1 H1 plus eta 2 H2 Hj components B F plus H1 H1 plus H2 J 1 2. So I simplified this notation. I just using simply use L to denote these vectors. Okay. Then because in the later computation I have to deal with two different components. Here this is a vector. Have two components, right? So that's why I write Lj into these Lj1, Lj2. So this first component, the second component. Okay? Now if you keep this in mind, then you can see this big system now can be written. And also one more thing is I just defined the G. So G is equal to 6. G is equal to Gx equal B. Okay? Use F plus eta 1 H1. Okay, so I use G like that to denote that. But remember, G also depends on eta 1 and eta 2. Okay, so then you can see this system can be written like this. Can be written like W eta 1 L2 G equals to W eta 2 L1 G. Then here is W eta 1 L2 perpendicular G equals to W eta 2 L1 perpendicular. Like this system. So now you can see this is a first order system. 2 by 2 first order system. Okay. So the key is that I can introduce a function W so that the derivative of these functions exactly equals to the X vector field H1 and H2. They are combined, considered as two different derivatives of a vector functions. Okay. So you can see this system. So here the next step is to rewrite this system. I mean, take a closer look at this system. So these are the vector functions, right? And this is the inner product under the matrix G. Okay, so rewrite the system. So this system can be written, finally can be written in the following form. So if I define W eta 1 and eta 2 is equals to, so these are vector functions, so now is using U and V to denote the different components. Okay, so then you will have the question, the system goes like this. It's U eta 1, V eta 1 times the matrix G is the L2 and L2 2 equals to U beta 2, V beta 2, G L11, L12. So that's the first system. Then the second system, you see the first system involves G, okay? And because in the product requires G, right? And the second system involves the perpendicular. The perpendicular, actually, you can have also have G minus, G inverse involved, so these cancel each other. So the second system actually is, second equation is simple. It's U eta 1, B eta 1 times minus L22, L21 equals to U eta 2 times minus L1 squared, L1, 1. So that's the system. Okay. Now you can see that this system, I mean, well, this coefficient very complicated, right? Coefficient. So the question, the unknown is W, involve two components, right? G is maybe also complicated. Okay. But however, this system is in 8 variable. So suppose in your plane, so you fix X, okay? You fix X. So X is no longer moved. So this system is regard to eta 1 and eta 2. Okay, so we can show that, but in general, there is a problem still have unknown. So there is a question is unsolved. So what kind of system is this? It's still it's unsolved. Okay. But however, in some cases, so in some important cases, we are allowed to take a close look at the system. Okay, so this means that in some cases, we can choose H1 and H2, okay, so that this system is elliptic. So it's not an elliptic equation, it's an elliptic system. Okay, and also, so now you can see that you have a solution to this. Suppose this case. Suppose we are talking about these important cases. Okay, so you can choose H1, H2. So therefore, the system become elliptic, right? So what can you do in order to get a conclusion? The reason is you have to take a look at the solution here. What is solution is omega, right? Right? Mm-hmm. Omega is the vector field. We can show that actually these are W eta 1 and eta 2 is bounded solution. R2. It's R2. So now you can think about how can we bring to our conclusion. If you have solution to the elliptic system, elliptic equation, which is bounded, what you can say. You can think about Lewis type theorem, right? So using Lewis type theorem, you can prove that this W eta 1 and eta 2 has to be constants. And eventually you can see that it's equal 0. Equal 0 meaning that the X vector field becomes 0, so this is exactly what we want. But however, at this stage, it's only found in some important things, not general. So that's the approach to this problem. Okay, any questions? I mean, the idea is quite, I mean, it's not simple, but however, it's quite logical, right? But however, one thing I like is we have to introduce all the symbols in order to express this clearly.
Notations.
Notation also problems.
What does it mean by the system is elliptic?
You have to show that electricity conditions.
Oh, so you mean like it's
Like-
bigger,
Yes.
the element is bigger than
Yeah.
0, okay.
The system you look at the determinant of
Yeah. That's right. Okay, AIJ.
Yeah.
it's a-
Actually, you can compute, so this electricity condition is coming from the computation of these coefficients, right?
Yeah.
So it turns out it's end up with, you can shoot this final quality. It's like this.
No, I just mean. I see it now. It's a matrix. It's the
Okay.
CIJ.
So
Yeah,
the
determinant
condition,
AIJ.
electricity condition here. Now, if you apply this concept, okay, if you do the computation, and you end up with the following, so the following is true. It's 4 L2 perpendicular G L2. So basically, this is in the product under the Riemann matrix, but I written down in the Euclidean case, so you can see the nature. So this thing is always pretty equal to 0. I mean, no matter what kind of direction you choose, no matter how what is a vector of these, so those kind of algebraic computation will show us this. Always will be given this, okay? But however, in order to get electricity condition, what this is always true, this is proven. This is proven. But in order to show that this is elliptic, you need this. No, without equal sign. Yeah. So you need this. But however, this one is not proven in the general setting. So this means that the system is not always elliptic. Okay, but however, so the things we want to prove, I mean, maybe a future research direction is that for a given F, that's a reference point, okay? And also, H is one direction. Find the H2. So where I'm given the H, that means I can treat this as H1. Then I know that the system requires second direction, right? So with the first direction, now you are trying to find the H2, okay? So that this system is elliptic. That's enough, okay? Because once I can search, I can get H2 from H1. Suppose given H1, I can get H2. Then I can show that the XF H1 should be 0, right? Okay. And this is enough because F is given arbitrarily, and H is given arbitrarily. And this shows that this morphism is independent of F. Okay, but I need to know for given F and H1, so how do you know that it is H2 to make this happen? Okay. So and if you take a closer look at this, and basically this means that you really need to show is that H1 is never parallel to H2 in under this matrix. Okay. Now, if this happens, if L1 and L1 and L2 are parallel, then this won't exactly become 0. When it's not parallel, then it's never equal 0. So that means that how do you control? So once the L1 is given, how do you find L2? okay, find the second derivative H2 in some way so that the corresponding gradient of solution is never perpendicular, is never parallel to the first solutions.
Okay.
It's gradient.
So,
So that's, I mean, it's come down very specific. Okay. But that's a very difficult thing to handle because the reason because really we don't know any more anything about the coefficient in detail because this coefficient in L1H2, remember, is always composite with the diffeomorphism. And that diffeomorphism is something we don't know. So what we really do is look at the structure, the coefficient structure, and do some algebraic computation. We come down to here, right?
so we want the inner product of L1 and L2 perpendicular to be bigger than 0.
You cannot have it. I mean, they're not parallel. You cannot have parallel.
This will give you the elliptic city condition.
Yeah, if this is not parallel, it's never parallel to that, then you get electricity
Yeah.
conditions. Yeah. Okay, so that's the entire story. There's some other work we didn't touch. It's more complete than this one. It's about also the possibility equation, I guess. So our equation, I have a gradient u here, right? So if I don't do that, I put u here, then put gradient u outside. You look at this equation. And this equation is simpler than that. And this equation you have a more general result. But however, the approach is very different. It's totally different approach.
Yeah, this is when you can take the second derivative.
Yeah, this one you actually you have to differentiate that, right?
Yeah.
You take the first derivative, and then also it turns out that you take the second derivative. The second derivative will give you enough information. But the problem is if you look at this equation, again, you take the first derivative, you're reducing it to the linearized case, the linear case, right?
Yes.
But here, you're taking second derivative is when you're getting more information about linearized equations. But here, suppose you do the same thing, you take the first derivative of this,
Yeah.
and then you take one more derivative. It turns out that the second derivative, starting from second derivative, is not going to get any more information. No more information coming from here.
So it's useless.
So that the only information is from the
First
derivative.
derivative.
Yeah. Now, if you can take third derivative if you want, you can increase the. Suppose you make coefficient more smooth.
Yeah.
You make a third derivative, fourth derivative. They are not going to give any information about that.
Yes.
Yeah. So that's the.
Yes.
Yeah, the reason I'm presenting.